in this series of videos or lectures, I'm going to build onto what is known as the Calabi-Yau space or a Calabi-Yau manifold, right? So this is just the part one in this lectures, and where I will briefly talk about complex geometry, right? Because there are some things that we would be needing to develop what is called the Calabi-Yau space. Now, what is a Calabi-Yau manifold? Well, it is a compact, complex scalar manifold that has trivial first Chern classes. Now, I know everything that I said right now might have went past your head, and that is exactly the reason that why we would be building onto the Calabi-Yau space. I will talk about every single word that I mentioned in this sentence, right? In these videos. So the question that you should be asking right now is why do we need to understand or study the Calabi-Yau space or a manifold? Well, one of the many reasons is that it is actually very important in string theory, where one model posits the geometry of the universe to consist of a 10-dimensional space, right? And you have something like it is in the form of M, which is a 10 dimension, sorry, it is your usual 4-dimensional space, right? And cross V, which is the 6-dimensional compact Calabi-Yau space. So M has 4 dimensions and V has 6 compact dimensions, right? Now, this in total makes 10 dimensions, right? Okay, and it is important to note that I'm talking about here are the space dimensions. You add your time dimension to this, and in total you have 11 dimensions, right? And that's why they say string theory needs 11 dimensions in total to work, right? Okay, so again, in this part of the lecture, I will talk about complex numbers, complex planes, and complex manifolds and tensors, right? Briefly. In the later videos, I will be discussing the complex differential forms, the Chern classes, the scalar geometry, and then, of course, uh, the Calabi-Yau space, right? Okay, so let's start off with complex numbers and what do you know about complex numbers, right? Okay, so you know in complex numbers, we have this idea of complex number arises when we need to define the square root of -1. So mathematicians did was is they said that square root of -1 is just defined with some imaginary number or iota, right? Now with this definition, with this simple definition, we can play with a lot of things in mathematics. Well, first we can define a complex number c as x plus iota y, right? Now this is your total complex number, but here it is important to note that x and y, they both belong to the real space. That is that x and y are both real degrees of freedom, right? Okay, what you can also do from here is that you already know is you can take the complex conjugate, that is c star, and all that does is it changes the sign for the complex part of the complex number. That is, it changes the sign with the imaginary unit iota. So you get iota y, right? Perfect. Okay, so now this c and c star, note that these both of these, they do not belong to the real space, but instead they belong to a space that is called the complex space or the complex plane, right? Okay, so you can well also do this thing. You can define the mod square of c something like this, right? As c times c star. So that is how the mod square is defined for a complex number. And if you do this thing, you multiply this thing with this thing, you get x squared plus y squared. So you can clearly see that this is belongs to the real space, right? Okay. Now let's talk about the complex plane, where first let me actually draw I'll draw the real plane, right? But what I'm talking about is the complex plane. I might be confusing you with this. Well, I'm talking about the complex plane, but let's look at the real plane, real space plane first, which is something like, say you have x over here, you have y, and this is of course your R2 because you have two dimensions, and a point in this plane would be defined with coordinates x and y, right? Perfect. Now if you look at well, look at this, that this x and y, there are 2 degrees of freedom, right? And in complex plane, that is sorry for my weird drawing, but anyways, y and x, and this is your complex plane, right? Where this c, it is c1, right? A point in this is defined as x and iota y, right? Where y is your imaginary axis, right? And x is your real axis. And you can clearly look at this thing, this definition of a complex number, which I wrote over here, that a complex number in one dimensions, that is c1, it has 2 real degrees of freedom, right? So what you can see from here is that, well, for R, for the real space, if I were to define R3, how would I do it? I would just take R2 cross R1, right? And this is 3 dimensions. For R4, I would do R4 as R2 cross R2, right? And this would be your 4 dimensions. But for the complex part, we have C2 as C cross or C1 cross C1. How many dimensions are here? Well, because each complex number has 2 real degrees of freedom, there are going to be in total 4 dimensions from this thing, right? So this has 4 dimensions. So C2 has 4 dimensions, where R2 has 2 dimensions. So what we can clearly see from here is that what we can do is we can exchange Cn and R2n, right? But both of these two are topologically non-trivial. What that means is they're infinite in all of the directions and they're flat. But things get more interesting when we make things compact. So by making things compact, what I mean is that you make their size finite and you make them curved, right? Okay. Now, for compact or curved real spaces, we tend to focus on what is called a special subset, which is known as a manifold, right? Now, roughly, manifolds are smooth spaces that locally resemble Rn, right? So that means that they locally resemble n-dimensional real space, right? An example would be S2, which in topological language is just your ordinary sphere, or sometimes also called a two-sphere, right? Okay. Now to make things a bit more precise for manifolds, consider this space, right? And we are talking first, let's consider in a real case where you would have x as n dimensions, right? Let's take x as n dimensions where x is real, right? And let's consider two pieces in this space which overlap each other. Let's call this one A and this one B, and this whole thing would be A union B, right? Now, on each of A and B, we have a map, let's say phi A, that is from A to the n-dimensional real space Rn, and likewise for B we have that takes B to some n-dimensional real space Rn, right? And on this A union B, this part, we have phi A composed with phi B inverse. It is a map from it is a map that takes Rn to Rn, but this belongs to some CP, where P is for a P smooth manifold, where usually P is taken to be infinity, right? For a smooth manifold, right? So all I'm saying is that if we have this R1, it is a manifold. But if I have this thing, if I have this thing, this is not a manifold, right? Okay, so now let's jump on to the complex case for with the same diagram, right? So let's talk about the complex case to develop the complex manifold. We would have the space, right? Again, and let's call it X again. But for a complex case, if you go back over here, we saw that we could do this thing, right? We could exchange Cn and R2n. So if I have over here n dimensions, then in this case I should have 2n dimensions. Again, this comes from the fact that I can write down my complex number as x plus iota y, where in a complex space x and y, well, these are real degrees of freedom, and there are two of them, correct? So we have 2n dimensions in the complex case. So the manifold in this case, it looks locally like Cn, where again we have these two pieces in this, that is A, and they overlap. You have B, and the whole thing is A union B. And again, in this case, we would have some phi A that takes you from A, that takes, well, A to a complex n-dimensional space, and B, phi B takes B to a complex n-dimensional space. And on A union B, that is this thing, we have phi A composed with phi B inverse. This takes complex n dimension to complex n dimensions, right? Okay. Now, if you look at these maps, right, phi A and phi B, they are holomorphic maps, right? And so this holomorphicity of the transition functions is actually a very big part of what sets these complex manifolds apart from the real manifolds, right? Now, what I'm saying is, well, perhaps you might be familiar with this in the case of the complex space, where you had F is a map from complex space to C complex space, and this thing is your function, right? That is f of x plus iota y, which is equal to v, which is a function of x and y, plus well, let's call this u, right? U, which is a function of x and y, plus iota v, which is a function of x and y. and this function satisfying the what I'm sorry, I don't know how to pronounce it, but I hope I get it right. The Cauchy-Riemann equations, right? And what are those equations? Well, it's a set of these two equations. Partial derivative with respect to x of u is equal to partial derivative with respect to y of v, and partial derivative with respect to y of u is equal to the negative of partial derivative with respect to x of v, right? So this set of two equations is what is called the Cauchy-Riemann equations. Now the whole point over here is that the complex space, n-dimensional complex space, can be thought of as a space with two n real dimensions, right? Or two n real coordinates, but with an extra structure, right? That is more rigid in this case, right? But the interesting point is that though we can always think of a complex manifold as a real manifold with this extra structure, we cannot take any old real manifold just we cannot take any old real manifold and just add this extra structure to it to make it complex. We cannot do that. To make it a complex manifold, there are some conditions that must be met, right? Okay, so well, first of all, clearly this is not going to work for real dimensions that has odd dimensions, right? Because this thing forces us to have even dimensions, right? This 2 factor of 2 here. And well, another point is, first, well, consider some j mu nu, which is a mixed tensor, or it can be a 1 comma 1 tensor field, and this thing a tensor field that has to satisfy this relation, that is j mu nu times j lambda mu, which is equal to the negative delta function lambda nu. Now this thing over here, it is the generalization of what we have, that is the iota square is -1, right? This thing is in your two dimensions, right? But this thing that I just wrote over here, it is the generalization of this thing in higher dimensional physics, right? So well, you can call this thing that is j mu nu, it is called an almost complex structure, and it can be defined for any real even dimensional manifold. Now let's do something. Let's construct a 1 comma 2 tensor, and let's say that it is n mu nu lambda, which is equal to let's construct it out of this 1 comma 1 tensor, right? Well, it would be j beta nu times partial derivative or partial beta j mu lambda minus partial lambda j mu beta and minus j beta lambda times partial beta j mu nu minus partial nu j mu beta. Right? Now there is a special name for this 1 comma 2 tensor, and it is known as the well, I hope I pronounce it right, It's known as the Neon-Haus tensor, right? Now, if this Neon-Haus tensor, that is n mu nu lambda, is equal to 0, then your j mu, well, this thing, it implies that your j mu nu, this 1 comma 1 tensor, is a complex structure, and we can view the manifold that is in question as complex, right? So this implies that j mu nu is your complex structure. So all you have to do is you have to calculate this thing, and that is your Neon-Haus tensor, and if it vanishes, then it implies that the 1 comma 1 j mu nu tensor, it is a complex structure, right? And therefore your manifold is complex. Now, well, with this now, let's quickly talk about the general tensors. And so we have just seen that j mu nu, we can think of it as a map from TP, and I'll tell you what I mean by this, TPM to TPM. Now, what this thing is, it is just a tangent space to M at some point P, right? Now, what that means is that it is going to act on a vector and it will return a vector, right? Okay, so at this point though, this TPM is your real vector space at any point P. For us to allow the complex vector valued functions, we need a complex vector space at each point P in M, right? So what we can do is we can take this TPM and take this take its cross product, tensor product with the complex space. Now what happens is that this the map j mu nu, it acts as or let's do this thing, that it acts as j mu nu j mu alpha v alpha, right, is equal to negative delta nu alpha v alpha, which is simply negative, if nu and alpha are equal, it is negative v alpha, right? So what I can say from this thing is, well, this thing is just j squared, right? So j squared on v is actually negative v. So what I have done over here is, if you look at this thing, we can say that the eigenvalues of j on v in this thing, that is TPM tensor product complex space, are the eigenvalues are, in this space the eigenvalues are plus minus iota. And boom, just like that, right? We have defined this iota square equals -1 in higher dimensions, right? So now what we can say is, we can call this TPM 10 and TPM 0 comma 1. These are the eigenspaces, right, with eigenvalues plus iota and minus iota, right? So these are the eigenspaces, ignore my writing, and these are the eigenvalues, right, for the corresponding eigenspace, right? Now each of these eigenspaces are actually isomorphic to the complex space C mu. And the complex conjugate to each other, right? And in fact, what we can do is we can decompose this thing, that is TCM, right? We can decompose it into TP1 comma 0 M plus T0 comma 1 M TP, right? We can write down this thing as this tensor sum of these two spaces. Now, this thing specifically, it is known as the holomorphic tangent bundle, right? And this thing, right, well, let me do like this, is known as the anti-holomorphic tangent bundle, right? Now, what we can do is we can similarly decompose the cotangent bundle as well. And the cotangent bundle would be the complex conjugate part of your M. So that would be T, C, M star, right? The complex conjugate. We can decompose it into T, P star 1 comma 0 M, and this tensor sum T P star 0 comma 1 M, right? And so finally we can consider holomorphic vectors, which are V alpha, and the anti-holomorphic vectors, which are V alpha, V alpha tilde, right, with a decomposition of a general vector, right? So I can write that down as V mu is simply equal to V alpha plus V alpha tilde, right? Now, in this way, we can similarly treat all the vectors and dual vectors indices of more general tensors, right? So I'm not going to bore you any longer with all of this stuff. I'm going to end this video over here. And in the next lecture on this series of Calabi-Yau manifolds, we will look at the examples of the complex manifolds, right? And I think in 2 or 3 more videos, we will completely develop what is known as the Calabi-Yau manifold.